All right, looks like we can get started. Welcome everyone to the AstroAI seminar. Today I'm very pleased to welcome Edgar Vidal from Tufts University. Edgar is doing his PhD there, second year at the moment, but he's actually originally from California, Southern California, with some roots in Mexico. And very pleased to welcome him today. He's going to be telling us about some cool project he's been working on with some friends of ours, actually, with Alex and Carol, about hierarchical simulation-based inference for lighters, in particular for applications in supernova science and regressing on some interesting physical properties. So, floor is yours. I encourage everyone to interrupt with questions, and other than that, welcome. Thank you.
All right, so hi everyone. So yeah, like Rafael said, my name is Edgar, and I'm actually a second-year PhD student at Tufts University. So I'm actually just down the road. So if you ever want to come by and visit the department, get to know some of the people there, and kind of learn about the interesting science that we do there, I encourage you to come, and happy to chat about anything afterward in terms of Tufts. But today I'm going to be talking to you about this hierarchical simulation-based inference modeling framework. And this is a project that I did with both friends of, I guess, AstroAI, called Alex Gagliano and Vera C. Okay, well, let's just dive right in. And so we are in a very interesting in-time domain astronomy. Essentially, we have fully immersed ourselves in the era of big data, and the deal was sealed with something known as the Vera Rubin Observatory. And essentially, like a few months ago, they released their first light. Basically, Vera Rubin is going to get an entire, sky survey over the next 10 years. Essentially, what they're going to do is they're going to image the entire southern hemisphere and study the variations that happen on timescale on the order of days to months and even years. And so the question becomes is, as we get more and more data, how do we actually, pick and choose which of these objects we want to follow up with spectroscopic observation? And so the objects that I'm interested in are supernova, but these fall under the umbrella of transient objects. So there are many different transient objects, and these are just going to be objects that evolve on timescale on the order of days to even months. Now, this is different from a galaxy, which evolves on the timescale of order like hundreds of millions of years or even billions of years. These are going to be objects that change within a matter of seconds. So in a blink of the eye, this is going to change really rapidly. And so here's a very interesting plot that's showing you the parameter space of transient objects. So on the y-axis here is going to be the pre-brightness of that object. And the x-axis here shows you the characteristic timescale. And so you can think of this of the parameter space of all the known transients that we have observed. And so different objects like supernovae fall in a unique region of this parameter space. Now, something to note here is that for things that are called superluminous supernovas, they have like a very distinct region of this parameter space, but it's very sparse. And what that's telling us is that we don't actually have a complete census and understanding of the diversity of known transient objects. Most importantly, there are these gaps that you see here. Now, the question is that are these gaps there because there's nothing physically allowed there, or are the gaps there just because we haven't seen it before? And hopefully with Vera Rubin, we're actually going to be able to discover and explore all of this parameter space. Now, the objects I'm interested in are supernovae. The way they work is that there's going to be some explosion, and that if you track the brightness as a function of time, they're actually going to get a dramatic increase in brightness over the course of a week. And then that brightness is going to dim over the course of a month. And what this is telling you is that if you want to study transient objects, you only have a matter of days to decide which objects you find most interesting for spectroscopic follow-up. And so with Vera Rubin, we're going to get something called photometry, essentially capturing the brightness as a function of time. That's really easy. But we're only going to be able to decide which objects to follow up based on its photometry alone. Because as astronomers, what we really want is to collect the spectrum of an object. And so a spectrum is simply the brightness as a function of wavelength, or you can think of wavelength like color. And the reason spectrum is so important is because it tells you a little bit about the chemical composition of the object of interest. And if you're studying objects that evolve on very short time scales, then maybe you want to say something about the chemical composition and how it evolves across different moments in time. So here you're seeing the photometry, but each of those data points corresponds to a singular spectrum you see. So all of these peaks and valleys, these wiggles that you see here are changing as a function of time. Now, if I'm going to be studying supernovae, and I'm going to be basing my decision on what to follow based on photometry alone, then I better have a good understanding of the different types of, photometric light curves I see. So let's look at the diversity of different supernovae. So in an isolated system, what happens is that as the star explodes, some amount of radioactive nickel-56 is going to be produced in the system. And because nickel-56 is a radioactive isotope, it's actually going to decay down into cobalt-56 and then eventually into iron-56. And what that means is that in this decay process, some of that energy is going to be injected into the system, leading to these two different characteristic timescales of evolution that you see here on this tail end of the soup. Now, that's an isolated system. You can imagine that, at the end of a star's lifetime, it's actually going to begin to shed its outer layers. And those outer layers is going to introduce some circumstellar materials surrounding that star. And depending on the mass loss history of that star, as the star explodes, it's actually going to interact with that circumstellar material. So eventually, as the star explodes, it's going to slam into the circumstellar material and actually ionize it and lead to different evolutions in the light curve that you see here. And so really, the way this light curve will evolve will be dependent on the density profile of the circumstellar material that surrounds that star. Now, in the past 2 decades, there have been an emergence of these very luminous, very bright supernovae. And what's really special about these is that you can't just explain them by nickel decay and CSM interaction alone. And so the theory is that there is some central engine injecting energy into the system. And so the idea here is that once the star explodes, that core is going to collapse into some neutron star, and this neutron star is going to rotate very rapidly. And actually, that rotation is going to inject energy into the system, leading to these long decay, these long-lived light curves that you see. Okay, so there's a whole diversity of supernovae, right? And so what we want to do is, based on these light curves alone, say which objects I want to follow. So that leads us to the inference challenge. Because what we want to do is we want to infer which of these objects are of most interest to us. So let me quickly go over the inference challenge. So first, suppose we have a set of physical properties. Typically, what one can do is you can forward model a set of observations using some fancy simulator. Now, this simulator could be some empirical model that maps you from your physical properties all the way to your observations. You could also think of doing some complicated hydrodynamic simulation where you have some initial conditions that map you to your observations. But of course, if you want to do inference, you want to go in reverse. Based on these observations alone, can actually predict the physical properties that describe that evidence. Now, a community standard in supernovae science is using something like MOSFiT, which is just a modular open source fitter for astronomical transients. Essentially, what this does is it simulates light curves given a set of observations, but it can also do the inverse. It can predict the parameters based on the observations alone. And so MOSFiT is very special because it's not fully a radiative transfer modeling code, but it uses some of the information from those modeling frameworks and tacks on some empirical relationships to try to get some inference on these photometric data points to say something interesting about the physical properties that describe these events. It uses something called Bayesian inference, which is really cool because you can get a whole constraint of the parameters that describe these events, right? But of course, in the era of Vera Rubin, we're going to have millions of objects that we're going to possibly want to follow. And so while this is really cool for a handful of objects, you're not going to actually be able to scale it up to the needs with these new imaging surveys. The next generation of imaging surveys are here now. We want something to do this inference technique really rapidly. And so let me just quickly go over this Bayesian approach because this will be important for the modeling framework I present. Essentially, you can use Bayes' theorem, essentially say what is the probability of getting some physical parameters given some observation. And you can always just set this equal to the likelihood times the prior, but don't ever forget about this evidence term. This evidence term is really important because it tells you what is the probability of observing your data. But who's to say you've even observed all of your data, right? Okay. Now, a trick you can do is you can evaluate this up to some constant using something like MCMC. But of course, when you do that, when you're fitting 1 to 3 parameters, it's really fun, especially the first time you do it and it actually works. But as soon as you get to 6, 7, 8 parameters, You're going to spend like hours on a single fits, come back to your computer and realize that fit didn't. That's not good. We need something to be able to do this really rapidly, right? So there's a lot of problems that come with that. And so the kind of the motivation behind my work is that is there some way I can approximate this posterior using some fancy machine learning methods? So here today, I'm going to talk to you about how we've been using simulation-based inference to kind of tackle this problem here. And so what is simulation-based inference? So simulation-based inference basically says, suppose I have some model that is described by this very complicated data distribution. Here, I'm just showing you two different happenings. Well, let's say it describes some model I'm interested in. Now, what if I don't know how to actually analytically write out that complicated distribution, but maybe there's some way I can generate some samples from that target distribution. And the idea with SBI is, can I learn the inverse mapping to take me to some approximation of the true data distribution by using the sample set? And so our goal here is, can we train a machine learning model that can learn this inverse transformation? Now, in the context for supernova science, that's going to mean setting some prior distribution over the allowed physical parameters, and then using something like MOSFiT to forward model a bunch of observations. And so the prior distribution will simply set some boundaries on what's physically allowed. And then the observations will form sort of a likelihood, because the likelihood is like, what is the probability of observing some observation given a set of physical properties? And then with SBI, what we want to do is train a neural network that is trained on pairs of observations and their associated physical properties to get some sense of the posterior estimate. And we'll use something known as a density estimator to do that. So what is a density estimator? So a density estimator could be something like a normalizing flow. And the basic idea is, suppose you have some complicated data distribution. You don't know actually how to write it out, but you know it looks kind of funky like this. It has all these peaks and valleys. So the trick is that you can start from a simple base distribution and figure out if there's some mapping to take you from the base distribution all the way to the target distribution. And so what I want you to do now is I want you to think back when you were a little kid. Maybe you have kids who have done this before. An equivalent problem would be, suppose you start off with some Play-Doh that you buy at a store that comes with a tin. Can I transform that Play-Doh into some complicated data distribution, essentially making a dinosaur out of Play-Doh? So if your target distribution is very simple, you can just use the change in variables formula, which says that the probability density of this function is going to be some inverse transform of that function times this Jacobian matrix. Now, don't forget your Jacobian matrix. It's really important because that preserves density. What that means is that the integral under that curve is going to equal to 1, but also make sure that this integration is also equal to 1. And that's really important if you want to evaluate probabilities. But of course, when your kids were playing with Play-Doh, or you were playing with Play-Doh when you were a kid, you didn't just go from the ball of Play-Doh all the way to this dinosaur, right? There's some compression, some stretching, some rolling of the Play-Doh until you eventually got to your target distribution. And so what we can do with normalizing flows is we can take a series of invertible steps, take them very slowly until you get closer and closer to your target distribution. Now, to formalize this, it's like saying I have some target distribution X and I have some samples for my base distribution Z, then there must be an invertible function that takes me in discretized steps all the way to my target distribution. And the reason this is important is because you can actually evaluate probabilities. And so this equation that you see here is the change of variables formula, but in log space. But the key thing is that if I want to evaluate if a sample came from the target distribution, then all I have to do is invert this function and evaluate its probability. And so the goal with normalizing flows is, can I actually minimize something known as the KL divergence between two distributions? Now, KL divergence is just fancy talk. Can I minimize the distance between two distributions, right? And so over here, you're seeing two very happy distributions because they're right on top of each other. And actually, if you take samples from both of these distributions, feed them through the inverted form of this discretized flow, you'll actually, get samples that fall and look like a Gaussian distribution. So you can actually evaluate probabilities that way. So that means is that if you're training a normalizing flow, you can actually just figure out, rather than try to learn what this minimization of the KL divergence, you can just figure out what is the log probability that maximizes that. Okay. Now, as your data distributions get more complicated, you might be tempted to take more steps, increase the number of steps. So you can take the continuous limit. where you actually, make infinitesimal changes across time. And so what that means is you can actually trace the evolution of your samples having this dx dt, and that's just going to be some velocity. Now, don't get too scared about this velocity term. It's just the same discretized flow, but in the limit where your transformations are infinitesimal. Now, if I have this ODE right here, I can just solve it with some integration and figure out the trajectory of my samples. And so here is a visualization of what that would look like. Start with some base distribution, and you figure out a flow that takes you all the way to your target distribution. Now, of course, if I want to, minimize the KL divergence, I want to maximize the log probability, so I'll need to enforce something known as the continuity equation. And so what the continuity equation tells us is that the probability changing as a function of time is going to be equal to the outgoingness or the outflow of probability-ness. And so hopefully you've seen a version of the continuity equation in your physics classes, maybe like fluid dynamics, or even when you were doing electromagnetism, learning about charge density and current. This pops up a lot. But if you haven't seen it, it's like saying if I stretch a rubber band, the outflow of the particles will be related to how fast I stretch out that rubber band. Okay. Now, after doing some fancy vector calculus, you can actually, figure out what the log probability is, but eventually you're going to lead to some term that is the integration of a divergence velocity field. But nobody has time to calculate divergences and integrations during training, so we don't want to do this. Okay. So while this is really good at approximating very complicated distributions, it's not really good at scalability, because you're going to have to be doing this under the hood while you're training this. And so a very interesting revelation came about like a couple years ago, back in 2023. And it's this idea of flow matching as a way to mitigate having to integrate a divergence of a velocity field. And so here's how it works. So suppose at time equals 0, you have samples that are found in your base distribution. And at time equals 1, you have the target distribution. What you can do is you can define some arbitrary probability path that takes you from the first distribution all the way to your target distribution. Now, the simplest path could be a linear interpolation between the two, but you can imagine that you can choose any path that you need. Now, if you set the path, say here, a linear interpolation, then that means that my learning objective is to figure out a velocity, a dx dt, that maps me from the initial to the final position. And so dx dt is going to be x1 minus x0, and essentially my training objective is going to be to learn a velocity field such that at each moment in time, my probabilities are actually flowing in the linear direction of the target distribution. And so the really nice thing about flow matching is that you would still have to solve an ODE, because you would have to solve this velocity here, but you would only have to do this after training. And that means that this is going to allow us to have a scalable framework to perform inference and try to get, a way to evaluate probabilities in the era of variability. Okay. Now, before I get to my models, one thing I'll add is that whenever you're doing simulation-based inference, a good thing to do is to perform a summary statistic of your data. And so what this means is if I have some time series data, which has brightnesses, times, and maybe some photometric bandpass filters, it's a good idea to try to compress this down to some n-dimensional representation. And by doing this, any learning that you do going forward is going to be based on this column vector rather than the data distribution. This is going to help the training objective make it very simpler and reduce the dimensionality of the problem. Now, the goal here is going to be minimize the data such that I don't lose a lot of information. The way I will know I did that correctly if my posteriors using the data is approximately equal to my posteriors using that summary statistic. Okay. Now, for time series approaches, you can use something like a convolutional neural network, but a one-dimensional one. Essentially, you're going to slide a kernel across the time series to try to extract the most information you can. You can always use a multi-layer perceptron, just a fully connected neural network. There's nothing wrong with that. It's not as good, but you can always do that. But what we do instead is we use a transformer for self-attention. So what is a transformer? So a transformer serves as the backbone of all of these large language models. What this means is that what we do is we input our data into this transformer network, and then what it does is tries to figure out across all time series what is the most important information in predicting the next. And so what this means that as the inputs, we'll put in our data, and then maybe at later times, it's going to try to predict how the light curve evolves based on some information of the past. So like, for example, how will my light curve evolve given I reach some maximum brightness, right? And so we have all of this, methods to try to extract the most rich information. But essentially what this transformer will do is try to compress all of this information into this n-dimensional representation here. Okay. So now we have all the pieces that are necessary to understand the modeling framework that I have. But basically, my goals with this Supernova project is one, can I predict the energy sources powering at events? Because if I'm interested in certain energy sources that I want to spectroscopically follow up, then maybe it's a good idea to know what the energy source is. Then I can figure out what the physical properties describing that event is. And if possible, can I find some interesting anomalies, basically saying, can I find something that is outside of the distribution that I actually understand? So let's look at the workflow that we created. And so the first step is we're going to simulate about 150,000 light curves. Each of these light curves are going to be described by different energy sources. So like nickel interaction, CSM interaction, and the presence of a magnetic engine. And then you can imagine that different energy sources will have a varying length in like the physical properties that describe them. So in order to actually like have a good training framework, we're going to summarize all these light curves into some n-dimensional representation. And then what we're going to do is we're going to do a multitask learning objective. So the first task will be, can we do classification? Can we actually classify the energy source, but based only on this n-dimensional representation? We want to figure out what is the energy source powering a supernova event only on this summary statistic here. Now, once we figured out the true energy source, or hopefully our best understanding of that energy source, we're going to feed it through a posterior network and using that flow matching technique to try to get a sense of what the physical parameters that describe that event. And so here we'll use something called flow matching, but we'll use a transformer neural network for this. And the reason we use a transformer is because it has a flexibility in the inputs and outputs. So this way we can actually enforce that our model will only predict the allowed physical parameters that describe that event. And then so our training objective here is going to be, some loss function, which is going to be equal to the loss of the categorical network and the posterior network with some weights. And you can figure out the weight by just tuning it. So trying to like do a parameter space exploration while you're training this. Now, once you finish, yeah.
So the flow matching transformer is independent from your transformer encode.
Yeah, I wasn't clear about that, but we kind of go on one step at a time. So the first step is a transformer that encodes our data into this row vector right here, or column vector. And then we'll have a categorical network that's completely separate, but then this transformer will be completely separate from that. We have two transformers. We have one to encode and one to predict.
And is that transformer the architecture that you're using in the flow matching to predict the velocity field?
Yeah, this is going to predict the velocity field, which is going to give us a sense of what the parameters that describe the signals. Yeah. Cool. Great question. Yeah.
I would say, what is the categorical network when separated there?
Oh, so this categorical network is basically going to use this n-dimensional representation to try to classify what that energy source is. So it's just going to use like a cross entropy loss to try to figure out what is the right energy source describing that event. And then the energy sources could be nickel interaction, CSM, or magnetar, or different combinations of them.
You have 3 different models for MOSFiT.
I have 3 different models. But I can also, since it's modular, I can have multiple different components. So I can do like nickel plus CSM, nickel plus magnetar, and all the combinations in that.
Trying to classify what's so.
Yeah, right. Cool. So yeah, so like I don't know, I think it's really cool because doing this is basically saying, can I classify the energy source and can I regress against the physical parameters? But doing this all in one. By doing it this way, you can actually avoid having to train 3 different models, but you can do this all in one, right? And so once you finish, you can actually sample the posterior, and essentially you can say what is the most likely energy source and what are the physical parameters that describe that event. So let's go from right to left and look at each of these different components more closely. And so the classifier basically looks at a light curve, and then it compresses it down to that summary statistic, and then it tries to evaluate the probabilities of some certain energy source. So here are the different combinations of energy sources that exist. And then overall, the classifier is 90% accurate, so it's able to classify the correct energy source most of the time. But here I'm showing you an example that our model is actually struggling. And so this example is kind of saying that this light curve could either be explained by CSM interaction or the presence of a magnetar and CSM interaction. And so the question becomes, is our model struggling because the model is not good? Or is there some interesting physics going on with this light curve? So with the categorical network, you can, actually start to think and question yourself whether or not this might be something you want to look forward to and spectroscopically follow. And so you can get more information about this by looking at the posteriors. So because the model was, predicting about 60% of the time that it was a CSM interaction, you can just sample the posterior for the different energy sources. And so here, I just want to highlight that the model is actually able to kind of, constrain all of these different models, physical parameters, which is really exciting. But remember that, like here, it was saying it could also be CSM plus magnetar. But with our model, we can actually sample the posteriors, given that it was actually a CSM plus magnetar. In this case, it wasn't, but let me show you what that is. So here, I'm going to overlay the posteriors that it was predicting for this CSM magnetar interaction. So the question becomes, is like, oh, well, these blobs that you see here are very shifted. Is there actually any physical, meaning behind them? Are they reasonable? Are these actually physically allowed? Some things to take away is that, for certain parameters, like this rho parameter and n parameter, that is very characteristic of the density profile of the circumsolar material. So this is actually saying that, oh, well, my explosion occurred in two different environments. Essentially saying like, oh, the environment was produced by two different explosions based on the same light curve. Now, to get a sense if these posteriors are physically meaningful, what we did is we sampled the posteriors for both the purple and blue blobs, and then we forward modeled them using MOSFiT. And so here, in thin blue and purple lines are the actual posteriors that we sampled. So what you can see here is that the posteriors look very similar to each other. It's actually very hard to distinguish between two of the models. And you can imagine that in the presence of noisy data, you're not going to actually be able to distinguish between these two models. And so the power behind this modeling framework is that if you see something like this that looks degenerate, then maybe this is something you want to spectroscopically follow, because you want to get a complete census of the diversity of populations and understand what the differences between these two models are. Now, let's go to the first piece, this learned shared representation. It's basically going to be our encodings or our embeddings. Now, the only reason I actually made those embeddings was to kind of make the learning objective a bit easier. But is there any interesting information we can extract from those embeddings? And so what I did is I took this row vector or column vector, and then I visualized it using UMAP. Actually, this time I used the TSE. And so essentially I have some, row vector, and I project it into 2 dimensions, and I visualize what it looks like. And so each of these dots corresponds to this set of light curves, and then I paint over what the correct energy source is. And what's really interesting is that these energy sources are forming distinct clusters in this parameter space. And so, there's some overlap, there's some, unique clustering going on. This is really special because I never once told it to do this. This wasn't my learning objective. My learning objective was classification and regression. But clearly, I have learned something interesting in the embeddings here. And then what we did, after the fact, MOSFiT has the ability of forward modeling some light curves that you see here. And these are going to correspond to TDEs. So tidal disruption events. Tidal disruption events is basically when a star goes, in the path of a massive black hole and actually gets ripped apart with the tidal forces between the star and the massive black hole. So those are clearly not supernovae. These are something that is known as outside of the distribution. But clearly you can see that they form a unique region of the parameter space. They occupy a unique region there. I just want to caveat, like whenever you're using things like UMAP or TSNE, you don't want to draw too many strong conclusions from this. You want to make sure that you use these for visualization purposes only. And then, I see clusters, but I don't want to just commit to that, right? So what we can do is we can quantify this data distribution of the latent space by learning a normalizing flow. And by doing that, I can actually evaluate probabilities, whether or not a sample belongs in the entire data distribution or in each of these given subclasses that you see. So this is what that looks like. So what I did is, upon learning that normalizing flow, I can use the light curves that I see, get its embedding, and figure out and compute the probability of falling within each of these little subclasses. Now, for this object in particular, it was described by the nickel model. And so thankfully, my model was actually able to predict that the highest probability is the nickel model. But you see that there's some high probability which corresponds to the overlap that you saw between the clusters. Now, it's very clearly not one of these models that you see here, so that's good that they're actually able to describe the data distribution. Now, let's go back to these TDEs I mentioned. So if I forward model in TDE using something like MOSFiT, you can see that they look very similar. The light curves look very similar, right? They look almost identical in shape, but the only differences I really see here is that the separation between the light curves is much greater in the supernovae than the TDE. But if I evaluate the probabilities for each of these different subclasses, you can see that per subclass, the probability is really low across the board. So per subclass, these are outside of the distribution, but clearly across the entire data set, this TDE falls outside of this distribution. And so by doing this, by getting some more information about this embedding, you can actually quantify probabilities, whether or not something falls in or outside of the distribution for each of these classes. This is going to allow people to actually say, oh, I have some light curves, is this something interesting that I want to go at? Cool. Now, that was kind of like the highlights behind the modeling framework. And I just want to caveat by saying this was, I just want to caveat by saying that these were simulations, right? So, you can only believe these up to some, extent because these are just simulations. And so really what we want to do is want to apply this modeling framework to real data. And so you can imagine that real data is going to be irregularly sampled because the way it works is that the telescope will take an image of the sky, come back a few days later and take another image, and then you do image subtraction to figure out if there is some signal, some signal for detection. But if there's some giant cloud that's in your telescope, you're actually not going to collect that data point or even actually have a huge error bar on that data point. And so this is what an actual light curve will look like. There's some spacing, some separation. You won't actually get all the photometric band passes. So we want to address this problem using real data. And so what we're going to do is we're going to use something called Sky Survey, which actually stores a lot of the observational conditions for observed supernovae. And so that means it's going to collect the signal to noise for different observations and even include the weather conditions that was observed. And so what that means is that we can actually take our simulations and actually tack on some realism to them. So that means all of my simulations were uniformly sampled, so I can actually pluck out and actually replicate the cadence or how many times I actually observed that data point and add some noise measurement to it. But thankfully, because we use a transformer encoder, our encoder is actually flexible in the number of inputs, which means that even though we have separation between our data, we're going to be able to actually still get those embeddings and do the classification and regression. So basically, our model is set up to do this. I guess we just actually have to add up all this realism to our simulations. And so pretty much that sums up all the work that I've been doing. I've been doing this work with Alex and Carol for a few months now, and we're pretty much at the stage where we just need to actually input some real data. And then the first thing we're going to do is test this with ZTF, which is a complementary imaging survey that's based in the Northern Hemisphere. But as soon as Vera Rubin, is fully operational, we can actually learn something about the noise properties of it and make our simulations more realistic. So we're pretty much at the step where we're ready to go for both of these. We just need to add the realism. So I'm going to leave some summary slides, but I'm super happy to take any questions.
Thank you, Edgar. That was a great talk. Very related to a bunch of people's work here. So I'm sure there's a lot of questions. Yes. Okay.
Yeah, thanks. I understood how with the transformer architecture you can account for the different cadences, the missing data.
Yeah.
Can you repeat how you plan to put in the errors?
Okay, so basically this Sky Survey stores all the observational conditions. So what you can do is you can feed in a simulation, like simulated data, and it's going to say, oh, if I observe this, supernovae at this time, 10 years ago, what were the observational conditions then? So it's gonna like basically add up all the photometric noise that it observed for a specific supernovae. And you can just tack on the errors that came with that. So you want to like kind of match the signal to noise that you have.
So instead of putting in kind of the size of the error bar for each of these time bins,
Yeah,
you basically put in metadata which describes the level of noise
Yeah.
on like a higher, on like in some higher statistic.
exactly. Yeah. That, well, this is kind of like, I think we talked about this last week. And so I think we got to the point where we started talking to these people on how we could do it, but that was kind of the basic idea, is add some metadata in the back end so that it can actually just figure out what the noise and observational conditions were. Oh, yeah, good question.
Other questions?
Yeah.
Yes, Sebastian.
Thanks. If you remove the classifier path from
Mhm.
your model, do you see a similar cluster pattern emerging?
Yeah, so, okay, that's a really great question because when we were doing this, we did this one thing at a time. So the first thing we did is try to get posteriors per model. And then we try to do classification per model. And then we did this in the joint. And we found that by doing this together, the embeddings are actually learning something. They're actually learning a lot more than when you do it separately. So the clusters were more like sparsed out and they weren't actually like separated as well. But of course, these are simulations, so the separation is kind of naturally expected. They were more like on top of each other. You couldn't actually distinguish between the two. And so somehow by actually doing this jointly, the embeddings are learning more information. Yeah, great question. Yeah.
Oleg, yeah. Go on.
Yeah, I have another question. In the posterior plot,
Yeah.
one could see that depending on your input model, you would have a different number of parameters.
Yeah.
So do you have some sort of a switch in there, basically depending on your classification head,
Yeah.
what it does that your flow matching
Yeah.
part puts out a different number of
Yeah.
parameters?
Yeah, so that's really good. So I guess the workflow after you train it is it gets your embeddings, right? And then first, before going to the posterior, it actually goes to this categorical network. And then whatever was the most likely energy source, the posterior network is going to condition on that.
Okay.
So if it says like it's CSM interaction, it's going to be like, oh, only look at things that are CSM interactions. And because we're using a transformer, that condition is going to be like, oh, CSM is described by 4 parameters, so only output 4 arrays. Yeah. Thanks. Yeah.
I didn't quite sense. So your flow matching is conditioned on the output of the categorical.
That's correct. Yeah.
The max probability event.
Yeah, that's correct. Yeah.
Exactly. You thought about like marginalizing over like multiple, say the probabilities of S. You got two similar
Yeah, so
measuring sources.
so that's basically you're asking if I have 2 different energy sources, can I predict the posteriors all at once?
Right.
Yeah, so that's what is going on here. So when you sample it, 60% of the times it says it's CSM, and then the other 40 is CSM plus magnitude. But when you get the posteriors, you get all of these in one. You get all of these in one. And so what we did here is we just separated them out. Like sometimes it says it's CSM, sometimes it says it's CSM plus magnitude. But you can imagine that they're joint, but I think the joint doesn't really mean too much because
Right.
the parameters will be mixed up, right? Yeah, they won't actually be sense. Yeah.
So it doesn't actually make sense.
So yeah.
So then you create one of these plots for every single event.
For every single event, yeah.
Okay.
I think the coolest one would be like, for whatever reason, you had 3 different components. For whatever reason, you would have just 3 different clouds right here, like all described by different events and different number of parameters that describe that events. Yeah.
So in that case, you need to do the classification at the same time. You're not done that as a separate network.
As a separate network.
Rather than doing the equation fast.
So just go down this way?
Yeah.
Yeah, I guess you don't need this. This is just a way for us to try to extract more information into this learn share representation. Because like I said, we did this in steps. First, can we do posteriors per model? Can we do posteriors in the joint? And then can we do this all? So we just found that the clustering was better when you did the categorical network attached to it.
This sounds familiar to what you told me once about adding a classifier to your embeddings and it separates them better, no? Do you see a correlation?
Maybe like the other ones would improve by the extra information you get by trying to do the classification.
Oh, are you saying you've done something like where you?
No, not the same.
Okay.
Sorry, I'm confused.
Yeah, well, yeah, it just turns out that adding a classifier just enriches the embeddings that I have, makes it more useful for us to use.
I did want to follow up a little bit on your anomaly detection.
Yes.
Parts.
Yeah.
Can you briefly explain again how is it that you use a flow
Mhm.
to sort of learn the probability of a object under a particular model? Because I think this really relates to something we have been also talking about here with some
Yeah.
people about what is an anomaly versus
Mhm.
what's an outlier. And so it's not only about finding objects that are rare under
Yeah.
distribution, but about finding objects that are rare according to distribution that comes from sort of model, what's
Yeah.
really unexpected
Right.
given the model. So I think that's what you're trying to address here.
Yeah. I think the first part is a more philosophical question. What is anomaly versus what is an outlier? The way we define an anomaly is something that is outside of our distribution of known physics. So, a TD, in this case, a tidal disruption event, is not something that our model knows. It only knows about supernovae, and clearly TDs are outside of the distribution. And then what the flow was trying to do is trying to learn what this data distribution looks like, because we can evaluate data probabilities by using a normalizing flow.
So you learned that directly on these two-dimensional
Yeah,
space?
no, on the embeddings. This is just
Okay.
visualization.
Okay.
Yeah. I think we had like 64 dimensions for the embeddings, and this is just two-dimensional visualization. And then we condition it on the energy source, so you can figure out probabilities per energy source. And so something that would be really cool is like, well, what if you have like a low probability for nickel? That means that it's gonna be very rare. Like it's not gonna be a common source that you find. So because it has a low probability, then maybe that's something you want to find because it's a rare event within each of these known subclasses. But here you're seeing that across all subclasses, it's clearly outside of the distribution. Yeah.
So that would be for the TDE.
Yeah, that could be for the TD, but you can imagine you could have other transients that have low probability of being in this supernova data distribution.
Okay. Anyone else? If not, I think Edgar will plan to spend a few more hours here. I've invited him to our meeting, but if people want to talk to him right now, you can get late to that meeting.
Yeah.
And then I'm gonna see him in the fourth floor over there, close to my office, if anyone wants to follow up. Let's thank him again for a really nice talk.